Okay, this week we're going to prove two theorems relating to limits and inequalities. Now that we're comfortable with epsilon delta proofs, they should be pretty straightforward. The squeeze theorem is one of those big theorems in calculus. It's a cool one. The first one is also about inequalities, and it's not necessary in order to prove the squeeze theorem, but they're closely related, so we'll look at both. So first, if f of x is less than or equal to g of x for all x in an open interval that contains a, except possibly at a, and the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m, then L is less than or equal to m. So this just says that if one function is less than another function at some interval around a, then the limit at a of the first will be less than the limit of the second. Okay, assume the opposite. Assume that L is greater than m. The difference law says that the limit as x approaches a of g minus f equals m minus L. And we know that because we're given that these two exist. So we're just subtracting g from f. Okay, so if this is true, then we can use the definition of limits to say that the function minus the limits is less than epsilon whenever x minus a is less than delta. So if this is true, then let's say that in particular, take epsilon equals L minus m. So notice that we're assuming that L is bigger than m, therefore L minus m is greater than 0. So therefore, because we know this is true, we have some number delta such that the g minus x minus m minus L is less than L minus m. Okay. Okay, now we're just going to remove the absolute value signs because we know that for any number a is either going to be less than or equal to the absolute value of a, right? Because it's either negative, in which case it's going to be, this is always positive, and this is either negative or positive. So we can just rewrite this without the absolute values. Okay, so this is a, and so a is always less than the absolute value of a. So we just replaced this with this. If this is less than L minus m, then this is definitely going to be less than L minus m. So now we can simplify this statement. If we add minus m and plus L to both sides, then these cancel and these cancel, and these cancel, and these cancel, and we have 0. So then we can add f of x to both sides, and we have that g of x is less than f of x whenever x minus a is less than delta. But that contradicts the original assumption that f of x is less than or equal to g of x. So our assumption here that L is greater than m must be wrong. Therefore, this has to be true. Okay, and the squeeze theorem. This is the one that says that if you have one function that's less than another function, and you're trying to find the limit of a third function that's between those two, then if the outer two functions touch, then the third one has to have the same limit as the outer two. So you're basically squeezing the value of the middle function. If f of x is less than or equal to g of x is less than or equal to h of x for all x in an open interval that contains a, except possibly a, and the limit as x approaches a of f equals the limit as x approaches a of h, and they both equal L, then the limit as x approaches a of g also equals L. Okay, proof. Let epsilon be greater than 0. So since the limit of f equals L, then there exists a delta 1 greater than 0 such that f of x minus L is less than epsilon whenever x minus a is less than delta 1. Okay? And then we can rewrite that to say that L minus epsilon is less than f of x is less than L plus epsilon. So f of x is in that interval. So by the same token, since the limit of h of x equals L, that means that there's a delta 2 such that h of x minus L is less than epsilon whenever x minus a is less than delta 2. In other words, L minus epsilon is less than h of x is less than L plus epsilon whenever x minus a is less than delta 2. Okay, so let delta be the minimum of those two. Okay, I think we're out of room. Let's go to the next page. Okay, so notice we've done this before. This is a common way of doing this. You find a couple deltas that will work, and then you just make your delta the minimum, because if you find one delta, anything smaller than that is also going to work. Your delta can be as small as you want it to be. There's a limit on how big it can be, but it can always be smaller. So just find a couple and then pick the smallest one. So in this case, we know that if x minus a is less than delta, then x minus a is less than delta 1, and also x minus a is less than delta 2, because delta is the smaller of the two. Okay, now we know that f of x is less than or equal to g of x, is less than or equal to h of x. That was given. And we also know that L minus epsilon is less than f of x is less than L plus epsilon, and that L minus epsilon is less than h of x is less than L plus epsilon when x minus a is less than delta. So if this one is in here and this one is in here, then it has to be that g is in between them. So it has to be that L minus epsilon is less than f of x, is less than or equal to g of x, is less than or equal to h of x, and h of x is less than L plus epsilon when 0 is less than x minus a is less than delta. So that means that L minus epsilon is less than g of x is less than L plus epsilon, right? Because it's in between. And that means we can rewrite that as g of x minus L is less than epsilon when x minus a is less than delta. And if that's true, that's the definition of the limit. So therefore, the limit as x approaches a of g of x also has to equal L, QED. And what that means is, if this is f of x, and then this is h of x, and this is g of x, if f is always less than h and g is between them, and at some point f and h equals 0, then g has to equal 0 too. That's all it's saying. Okay, let's look at one example. The limit as x approaches 0 of x squared times sine of 1 over x equals 0. Let's show that that's true. So first note there's a product here. Notice that we cannot use this because the limit of sine of 1 over x does not exist. Remember, this is just like the one we looked at last week with pi over x, where it goes up and down, but it keeps going faster and faster. So there is no limit to this part. So we can't use the product rule. This is why the squeeze theorem is so amazing, because even though this limit doesn't exist, we're still going to be able to show that this whole limit still is going to equal 0. We're going to squeeze it. So we do know that sine is always between minus 1 and 1. So we do know that, that if we multiply x squared throughout this, we have that minus x squared is less than or equal to x squared times sine 1 over x is less than or equal to x squared. So this is interesting because these are both just parabolas. This is just y equals x squared. And this is y equals minus x squared. And so this is between these two. And even though we know that it's getting more and more sort of violent as it comes in, and same on this side, something like this. Even though it's getting more and more spastic, it's also being squeezed down to a point so that at 0, it's going to be 0. So to write it down, we know that the limit as x equals 0 of minus x squared equals 0, and the limit as x approaches 0 of x squared equals 0. So if we let f of x equal minus x squared, g of x equal x squared sine 1 over x, and hx equal x squared, then using the squeeze theorem, we know that okay, that's pretty cool. All right, that's good. Next week, we will learn about limits involving infinity. Then we'll study continuity, and then we'll move back to apply what we've been learning here to multivariable, continuity, and limits, and so on. And then we'll move forward with multivariable differentiation. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.